Hello friends, hope you are having a fantastic day today. So now we are going to do a very popular LeetCode problem called LRU Cache, and this is a very well liked problem and it is a LeetCode medium problem. Now this problem can be asked in two manners. This is a very popular system design constraint as well. It's very simple for a system design, but still it is there. And also it is a LeetCode problem, so it can also be asked in your technical interview. So I ask you to put higher attention to this problem because it can be asked in two different types of interviews. Now let's understand the problem statement. Basically, we need to create a data structure that follows the constraint of a least recently used cache. So first let's understand that what are going to be the constraint for the least recently used cache. The simple thing is, purpose of cache is to store some values. Let's assume that currently we have this cache and we can store 3 values inside the cache. So the idea is that first I add value number 1, then I add value number 2, and then I add value number 3. Now because value number 1 was the very first value that I entered, or it is the least recently used item in the cache, because relatively number 2 and number 3 have been used after number 1 was being used. So number 1 is the least recently being used value. So if I have to add value number 4 inside the cache, I need to kick out 1 and I need to add 4 over here. But in this scenario, now the least recently used item is going to be value number 2. And if next element is 5 I need to enter, then I need to kick out 2 and add value number 5. But currently now this 3 is the least recently used. But say for an example, for some reason I ask this cache that, hey, get me this value number 3. In this case, now this 3 is no longer the least recently used value. Now the least recently used value is going to be this value number 4. So in case if I have to enter value number 6 in this case, now again I'm going to kick out value number 4 and add value number 6 over here. This is the constraint of least recently used cache, and this is what we need to implement. But now let's go back to our problem statement and understand what exactly being asked us to do. So number one thing is, we need to create a class LRU cache class where we need to implement few methods. Number one method is a capacity method. So the capacity method defines that this is going to be the size of cache. So in this case, currently our capacity is 3, and this is what we come up with. Okay. Next one is that we need to create a method that gets any particular element from the key from our existing cache. Now the thing is, the value we are storing inside the cache is actually a key value pair kind of the thing. So in the input we would be given values like 1 1. So in this case, the value we need to store is a key value pair, that is 1 1. This is the whole node where 1 is defined by the key and its subsequent value is value number 1. Okay. Now, in order for us to put the value, now if we have to add a new value inside our cache, then we are given some more constraint. Number one constraint is that we need to update the value of the key if the key already exists. Okay, so that is number one constraint. Number two constraint is that if the key does not exist, then we need to add the whole key value pair inside our existing cache. And for some reason, if we move out of the capacity, then we need to evict, or we need to kick out the least recently used key. So the same thing that we just saw in the example. Okay. So now let's try to understand this whole scenario with like a slightly broader case, and we will try to understand that what are the things we need and what are the constraints we have and how can we actually start implementing these methods. Now, for all of you, I must know that the moment you heard that we are using key value pair, the number one thing that comes to your mind is that we are actually going to use HashMap, and you are exactly correct. In order to store all the values inside the cache, we are actually going to use the HashMap. Now the thing is, in the HashMap, the typical structure is that we have a key and we have associated value. Now in this case, the node we are trying to store, the node is actually structured as a key value pair in itself, and this is going to be the value, and the key is going to be the same key that we are being given inside the node that we are going to use. But one different thing we are going to do is that instead of storing, let's assume that currently the value of this node is that key is 1 and value number is 5. If this is the value we need to store, we are not going to store it like this, that number 1 as the key and value as number 5. No, this would be correct, but we will not do that. Instead, what we would do is we will see that what is the pointer location of this node, and we are going to store the pointer location that points to this particular element, and it would be the same thing because we are using the hash map. So access is always going to be big O of 1. We can always find this value in big O of 1 time, but this is going to be greatly helpful for us in order to maintain the order in which the elements came in. This is the most important part, because we are not only storing the values inside the hash map and kicking the values out of the hash map, we also need to keep track of that what was the least recently used item, which means at the same time we will also have to keep track of that which was the most recently used item because of the get operation. You understand my point? That what I'm trying to say, because remember, we need to implement 3 methods. Number 1 method is a capacity. Now capacity is really easy to make sure, because that is going to be the size of our hash map that we are going to implement. So we will never be able to exceed our capacity. That is number 1, that has been taken care of. Second method is the put method. Okay, put method is also relatively easy, that I just explained, that we as a key we are going to store the key, as a pointer we are going to store the node that we are going to point. Next method is the get method. This is also very easy, because we know that in the get we are being asked that hey, this is the key and fetch me the whole value. Now inside the hash map it is really easy to fetch out values. We can do that operation in big O of 1 time. Let's assume that currently we have a value like 2 and its subsequent pointer that points to the value of 2 and 5 in the node. If we are being asked to fetch this value, we can fetch it very quickly in big O of 1 time. But the problem is, when we have to, for this put operation, when we run out of the capacity, then in that scenario we will have to do an eviction. Now for this eviction, we need to keep track of that what was the least recently used element that we came up with. And in this case, first instinct is to use a simple queue, because let's assume that for a second we don't have this get operation. Okay, let's assume for a simple second. Now what would happen is, currently we have our hash map. Now inside the hash map we need to store the values of key value pair. Okay, and what we are going to do is, let's assume that the current capacity is 3. Okay, so let me add 3 blocks. Same way the current capacity of the queue is also going to be 3. Now number 1 thing is, first value we are trying to enter is 1 1. So let's assume that I'm entering value 1 1 over here. Same way the very first entry I'm going to enter inside the queue is going to be 1 because of the key. Second value is 2 2. Once again second value is 2. Next value is 3 3. Once again the value is 3. Now let's assume that there is value number 4 I'm trying to insert. What value should I evict? It's very simple. The very first value that entered inside the queue has to be the first value that gets kicked out of the queue. So this is very simple to implement. But the problem is that currently this sequence is fine, but the moment I apply the logic of get, now in this scenario, let's assume that I decide to get value number 2. Okay, let me add this value number 4 before. Okay, so let me go ahead and quickly do that. Okay, I added value number 4 over here. I also got rid of 1 and I adjusted the flow of 2 and 3. Okay, so now I adjusted the flow of 2 and 3 and 4, and now I have already added the value number 4. Now the thing is, I apply get operation. Currently in this scenario, the least recently used element is value number 2. That is very simple to understand. But now if I do get 2, immediately 2 becomes actually the most recently used element because I just accessed 2. So now what would be the new flow of the queue is that it's going to be 2, 4 and 3. And now suddenly 3 becomes the least recently used character. And in this case, if I have to kick one value out, I can also kick that out. Basically, if I want to add value number 5 in this case, now I need to kick value number 3 out. Now the question is, you must be thinking that, hey, even with the queue, we can actually implement the same thing. What we will do is, whenever we are being asked to run a get operation, all we need to do is we first need to find the value that is currently present inside the existing queue, move it to the very first element of the queue and shift all the other nodes one step forward. And then also this logic would work. But that would be a suboptimal approach. Why? Because HashMap is going to run in big O of 1 time. No issues with that. Queue, typically it is going to run in big O of 1 time because we are simply popping elements out from behind the scenes. But when we have to do the get operation, we need to iterate over the entire queue in order to find the position of that element. And that operation takes big O of n time. And if we see the problem statement, we are very explicitly being told that the functions get and put must run in on an average big of 1 time complexity. So we need to take care of that scenario. So now let's just break down the same problem and try to come up with the thinking that what are the things we need, what are the things we have, and how can we make the solution better. This is the approach you should be thinking in your actual interviews as well, and that is why I created this whole 10-minute preamble of the whole things that we are now going to come up with the optimal solution. So in this case, once again, we already mentioned few things, that we are using HashMap in order to store the values. Now you will understand that why instead of using HashMap to store just the values, why am I storing the pointer of that particular value? Now it will come to your senses. Okay, what I'm suggesting is that currently, remember, we need to keep track of 2 items. Number 1 item is what is the least recently used item. Number 2 item is the moment we use the get operation, we also need to keep track of what is the most recently used item. And there is going to be all of these bunch of different elements that fall between each other, but basically the moment we are accessing any particular element, that becomes most recently used element. The moment we want to kick out any element, we kick it out from the least recently used element, which means we need a data structure where we can actually work on both sides of the queue to either enter the value or remove the value, and we need to do it in fast and efficient manner. And for that, the very simple thing is one of the most basic data structure, that is a linked list. But this is not a simple linked list. We are actually going to use a doubly linked list. And how this doubly linked list is going to help us to solve all of this issues, let's think about it. So now let's understand that suppose currently this is our hash map where we are storing all the values. Let's assume that this is our doubly linked list. Okay, and currently for our hash map, once again the capacity is 3. Now why are we using pointer instead of actually using the value? That will come to your mind very quickly. So let me just add few values. Okay, number 1, number 2, and number 3, these are the 3 values. And let's assume that for these 3 values, I'm marking as pointer 1, pointer 2, and pointer 3 as the 3 nodes that contain all the information. Now once again, I'm marking these 3 nodes over here, pointer 1, pointer 2, and pointer 3. Okay, and currently inside our doubly linked list as well, because we added values sequentially in the same sequence, we are going to have, okay, so this is our least recently used item and this is our most recently used item. Okay, now the very first item we have in the least recently used is going to be pointer 1 or the value 1 or the node 1. Okay, you can think of it, all of these things. So basically value 1 and 1. Same way, second is going to be P2, basically value number 2 and 2. And third one is going to be pointer 3, that is going to be 3 and 3. Now the thing is, where this pointer would come into useful is when we have to change the positions, because same logic will come to your mind that, hey, in the queue, why we were not using queue? Because in order to find any particular element, we had to jump through all of these places, and that was causing big of n time. But in this case, we have the additional benefit that because we have the hash map, based on any particular key location, we can directly find that where is that particular value is located inside the existing queue, and all we are concerned about is to storing least recently used and most recently used values. So now we are going to start manipulating these values. So let me just clean this up a bit, and now we are going to start working our magic. Now let's assume that currently we need to add value number 4 in this case. Okay, so we are going to add value number 4 over here. Once again, now the logic is quite simple. We are because least recently used value, we already know that is P1. We are simply going to get rid of it. But now what we need to do is we simply need to say that whatever the value, that is because we removed the least recently used value, which means we removed the head of the existing linked list. So the moment we remove the head of the existing linked list, automatically the second value becomes the least recently used value. So now we have P2, that is least recently used currently. Next value is going to be P3, and then we are going to have value number P4 as the most recently used value. So let me update those values. So P3 and P4. Okay, currently we have these values associated, and subsequently we have pointers that point to those correct values. Now let's assume that for some reason we decide to access value number 3. Okay, we create another operation, that is get operation, get 3. Now the moment I do get 3 operation, suddenly now even though 3 is in the middle, what I will do, in order to do the get 3 operation, first I'll do that whether key number 3 exists inside the hash map or not. Yes, it exists. If it exists, all I need to do is I need to fetch the value of the 3, so I can simply return that. But at the same time, I can go to this pointer's location and I can say that, hey, whatever your pointer location is, now you need to jump to the head of the to the tail of the linked list, because currently now you are the most recently used value, and that can happen in big O of one time because it's a doubly linked list. So we are just going to use the same logic, and now in this case P4 becomes our second least recently used value, and P3 becomes most recently used value, and we are able to find this value because we are using pointer. So we are avoiding the scenario where we have to iterate over every single value inside the linked list and saving up on the time. Okay, now for the same scenario, let's assume that instead of this, now we are trying to add value number 5. Okay, so if I want to add value number 5, I need to kick out least recently used value. I already know least recently used value is P2, and in the P2, because I'm storing the whole node, it contains the value as 2 and 2. So all I need to do is that whatever the head position has the node, I just need to go to that key position, and the moment I go to the key position, I simply delete or remove that key. So now I'll get rid of this 2. Okay, I'll also get rid of this 2 over here. Now my least recently used is automatically going to adjust. That is going to be P4 and P3, and now there is going to be P5 as the most recently used because I can easily manage that. And in this scenario, now once again I need to enter the value 5 and P5 over here, and that's it. This is the whole logic of least recently used test case scenario, and you can add as many nodes as you want, the logic will remain same. And now let's try to understand time and space complexity. Time complexity, pretty simple to calculate. We are using, okay, so let's assume for capacity it doesn't matter because it is like we are just allocating some value, so this does not take part in the time and space complexity scenario. Now let's assume for the get operation. So what are we doing for the get operation? If we want to get any particular value, get 3, let's assume, we are going to check that whether this key exists inside the hash map or not. Yes, it exists. Now we can easily fetch the value from the pointer, there is no issue with that, but at the same time we will have to mark 3 as the most recently used value, and that can also be done in big O of one time, and this hash map can also operate in big O of one time. So get operation now works in big O of one time. Awesome. Now let's take care of the put scenario. Once again, for the put scenario, we will also have to repeat the same thing. Basically, let's assume that now we have this value number 6 we need to add. We realize that the capacity is full. So because capacity is full, we are going to go to the hash map first, take whatever the head position is, find what is the key associated with that because it stores key and value both. And this key contains the value number 4. So go to value number 4, kick value number 4 out, add value number 6 over here, and that's it. You solved the problem. And now this operation also happens in big O of one time. So this is the whole approach. Now let me quickly go over the code. Now let's look at the code for our problem LRU cache. So first thing we are going to do is we are going to create a static class node where we are going to store the definition of the node that contains the values key and value. On top of it, we are going to keep track of the previous node and the next node for any particular node, and this aligns with our doubly linked list concept. We also have a simple constructor to store the value of key and value that comes in as the put method. Now we have some variables that we need to define. So first variable is the capacity. Next one is a hash map. Now inside the hash map, as a key, we are going to store the integer value of the node, but as its subsequent value, we are actually storing the pointer of the node and we are pointing it to the element that we needs to put in. This comes along as we understood during the explanation. And then we have two dummy nodes that are head and tail, where head is going to keep track of the most recently used and tail is going to keep track of the least recently used element, and then we can simply manipulate those values. Next thing is this is the method in order to instantiate the capacity. So it is a very simple method. All we are doing is just creating a hash map of the same size. On top of it, if we have to, let's understand the logic for the get method. in which we are given the key as an input. So first thing we are going to check is whether this key exists in the hash inside the hash map or not. This we can do it in big O of one time. If it doesn't exist, we can simply return -1. If it do exist, we can simply return the node value. That is perfectly fine. But before that, we need to create, or we need to put it as the most recently used value. So what we are going to do is we are going to instantiate a temporary node that is going to be associated with the given key. And for that, we are going to remove that from our doubly linked list, and we are going to put its position as at the head value. And both remove and insert at head values, I have created helper method for those. So this is the remove method and this is the insert at the head method. These are just very basic pointer manipulations inside our existing linked list. Now going back to our get method. Now in this scenario, and in the end, once this node has been mentioned as the most recently used node, then we simply return the node's value. So that fulfills our get method. Next, let's understand the logic for the put method. That is slightly more complicated. We are given the two input values for the node that we need to put in. Now, first thing we are going to do is we are going to check that whether this existing key already exists, and if it does, we simply need to update the node associated with that. So if it exists, all we need to do is just assign a temporary node. Whatever the value of the new node is, assign that to the existing value for our existing HashMap key. And then we need to remove that node pointer and insert it at the head, because now this becomes the most recently used value. If that is not the case, and we need to enter the new value all by itself. So first we are going to check that whether we are running out of capacity or not. If we are running out of the capacity, we are simply going to remove the last element that exists at the tail. So that we can simply do it in big O of one time, because we can already always find that what is the value associated or at the least recently used using our doubly linked list. And then we can simply remove that value. And then we can simply add a new, in either case, now we simply need to add a new node inside our existing hash map. And after adding this new node, we need to add this new node at the head, because now this becomes the most recently used value. So I know that this code looks like a little bit complicated, but overall the simple logic remains the same. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions in terms of time complexity, and also great in terms of space complexity. So once again, I will be posting this code inside the GitHub repository that we have, and you can check it out from there. Let me know in the comments, what do you think about this video? Do you think is there anything else I could have done to make it better? I'm always open for the feedback. So thank you so much for that. Until then, take care.